Hi, so in this video we are going to discuss about linear phase transfer functions. So what are linear phase transfer functions? Linear phase transfer function means we have got same delay for all omega, right? We have got a transfer function or a system h e to the power j omega. The input is some x of n and the output is some y of n. So what is an example of a linear phase transfer function, which means same delay for all omega? This means my y of n, let us say, is simply x of n minus some capital D, some delay. So this is a simple example of linear phase transfer function. You see, the delay for every frequency is same. Basically, this is just a shifted version, right? My y is just a shifted version of x. This is an example of a linear phase transfer function. So let's generalize it. So let's take a z transform. Y of z is equal to z to the power minus d x of z, or if you want to take the uh, h e to the power j omega, okay, let's say y e to the power j omega is simply e to the power minus j omega d x e to the power j omega, right? So what do we see here? So this is my transfer function, or h e to the power j omega, my system. For this system, my angle of h e to the power j omega, this is equal to how much? This is equal to minus omega capital D, right? This is also called theta of omega, right? Now, what is my phase delay? Phase delay is simply minus theta omega upon omega. This is equal to capital D. What is my group delay? This is equal to minus d theta by d omega. This is also equal to capital D, right? So this is a linear phase transfer function. Basically, my phase term is of this form. It's linear. The phase, this is linear phase, right? So I want to highlight this thing, and this is linear phase. Okay, so with this motivation, let's go to the next. Let's define the properties, or let's look at the properties of linear phase transfer functions. So so we are now going to discuss about finite impulse response linear phase transfer functions. Okay, so what is the meaning of finite impulse response? Finite impulse response means my h of n is finite, right? My h of n is equal to something. Basically, it is equal to 0 for n less than 0 and n greater than some finite number capital N, some finite integer capital N, right? So this is basically my h of n is it is there for only a finite number of capital N, and rest everywhere it is 0. This is my h of n, this is my n. This is a finite impulse response. So what is the h z for this? H of z will be equal to summation of h of n z to the power minus n, where n can only go from 0 to capital N, right? This is for FIR filter, finite impulse response filter. Now, what is the meaning of linear phase? Linear phase means my h e to the power j omega, the angle of h e to the power j omega is basically linear. What does that mean? It means this is equal to some constant c times omega plus some beta, right? Is linear in omega. You can also call this is your theta omega. Okay, so let's combine the two things. So what is the general form for my h e to the power j omega? So general form will be e to the power j c omega plus beta, right, times some a e to the power j omega, where this is a uh, real function. This is the general form for my linear phase transfer function. Now, can we put some more constraints? Okay, let us say if my h of n is real, right? Because that is what generally we do for real h of n. This implies my h e to the power j omega star will be equal to h e to the power minus j omega, right? This is the property for real h of n. Can we combine these properties to see some um, useful properties in h of n? So my question is, the quest is uh, how h of n looks like, or I think what h of n looks like. So let's use these properties. So what is my uh, let's substitute from my previous equation the general form of h e to the power j omega. So substitute h e to the power j omega is equal to e to the power j c omega plus beta times a e to the power j omega, right? So let's see how it looks like. So this becomes e to the power, so I will move the star here and remove it from here just for simplicity. E to the power j omega c plus beta times a e to the power j omega. This is my h of e to the power j omega. This is equal to h star, so which means e to the power minus j times c, and then there is a minus omega because omega also is negated, plus beta times a star e to the power minus j omega. Now you know this is real, so therefore the star does not play any role. So now this becomes my c omega and c omega get cancelled in both sides, so it becomes e to the power j beta times a e to the power j omega is equal to e to the power minus j beta times a e to the power minus j omega. Now there are two possibilities. One possibility is that, so case one, that a e to the power j omega is as an even function of omega is equal to a to the power minus j omega. This is an even function. So this is the case one. So what will happen in that case? E to the power j beta is equal to e to the power minus j beta, right? And that means my beta, or e to the power 2j beta, is equal to 1. This means my beta is equal to, okay, this implies beta is either 0, so 2 beta is either 0 or pi, or 0 or 2 pi. So this implies my beta is equal to 0 or pi. And what is the case 2? Case 2, so this is an even function. So, and case 2 is my a e to the power j omega is minus of a to the power minus j omega, which means it's an odd function. So what does this imply? E to the power j beta is equal to minus of e to the power minus j beta. This means e to the power 2j beta is equal to minus 1. So which means my 2 beta is equal to how much? Pi or minus pi? So which means my beta is equal to minus pi by 2 or plus pi by 2. So basically plus minus pi by 2, right? So these are the two cases which I have obtained. Now let's look at these cases in slightly more detail. Consider case 1, where my a is even. So what happens in this case is, now I want to see what is the, how does my, or what does my hn looks like. Now to go to hn, I have to go from h e to the power j omega to hn. How do we do that? Okay, so let's start with the basic definition. H e to the power j omega is equal to summation of hn e to the power minus j omega n. N goes from 0 to capital N. This is the basic definition of my h e to the power j omega for a finite hn, finite impulse response function. Okay, now let's try to put some properties. So the h of e to the power j omega is equal to what? This is equal to some e to the power j times c omega plus beta times a e to the power j omega, right? And this is equal to summation, basically the whole thing. I won't write it again. So let's do some simplification. Let's take this part to the other side. My a e to the power j omega becomes equal to, this is e to the power minus j beta summation of hn n equal to 0 to capital N e to the power minus j omega n, and remember there is also minus j omega c, so this becomes plus c, right? Now we have defined for case 1 my e to the power j beta, which means beta is 0 or pi. So if by beta is 0, this is 1. If it is pi, it becomes minus 1. So this is plus minus. Both possibilities are there. Summation, this thing, right? I think this part is clear. Now, again, let's take a minus omega. Okay, okay, now we can use a e to the power j omega is equal to a e to the power minus j omega. What does that mean? So my a e to the power minus j omega will be equal to, this part does not change, n equal to 0 to capital N h of n e to the power, so minus j times minus omega, so it becomes plus omega n plus c. Okay, now this is something interesting. Let me do some trick here now. What I want is, I want to convert to right negative sign. Okay, so now I want to match these two terms. So put n is equal to capital N minus L, right? Where L again goes from 0 to N, right? that does not change it. So this is equal to plus minus summation L equal to 0 to capital N h of n minus L e to the power j omega n minus L plus C. Right? So now we can compare the two terms. Okay, let's compare the two terms. Let's compare these two. So what do we get? If I say these two are equal, so now now you use again, so maybe I will write equation number 1 and equation number 2. So now equating 1 and 2, what do we get? We get h of n is equal to h of n minus L, sorry, capital N minus, let us replace L with N only because L is a dummy variable. So, and then the phase term also should be equated, which means my e to the power, so which means my e to the power j omega n plus c with a negative sign. This is equal to e to the power j omega n minus, oh, let us replace this with a small n, it's a dummy variable, plus c. So what do we get here? We have to simplify the e to the power terms. So this is j omega n and n, they get cancelled out anyways. And what I get is j omega minus c is equal to n minus c. So what does this give me? This gives, sorry, n plus c. So this gives me c is equal to minus n by 2. Okay, so these are some important results now. Okay. Yes. Yes, I think this is, and also we have seen earlier that my beta was 0 or pi. This is again an important result. Okay, so these are the possibilities. And similarly, if we do for the odd case, let me do it here itself. Let's say with a yellow pen. So if it is odd, then what will happen? Then this thing remains same. My e to the power j omega, this becomes negative, right? So this will become, so okay, let us say this also does not change. Only here, instead of equating, it will become a negative sign. So you will get, this will be negative, and this will be pi by 2 or minus pi by 2. Rest everything else remains same, right? For the odd case, right? This is this negative here. Okay, so these are the cases, these are two possible cases. So based on these, we can define 4 kinds of filters. So let me write down, I think in the slides you can see there are 4 types of filters defined. So let me go to this figure, which you have in your, yes. So one is where you have symmetric A, right? My A is symmetric or it's an even function, and when it is odd function. If it is an even function, what will happen? My h of n is equal to h of capital N minus n, right? Which is here. Let me show you the properties. So you have here h of n is equal to h of capital N minus small n, right? That's what you see here. And then you see my c is minus n upon 2 and beta is 0 and pi. Okay, I think those things are not visible here directly, but this is visible, right? And another possibility is that when my length of my filter is even, which means my capital N is odd, like it is 3 in this case. Okay, and then we have antisymmetric when my a of e to the power j omega is an odd function. Then these are the possibilities. So basically my h of n is minus hn minus l. So you can see it's h of n is h of n minus n. And again, two possibilities when it is of odd length or when it is of even length. Now we will discuss these two things in a bit more detail. Okay, let's do that. So let's start with the first case. Or let's do it in the next video. So thank you very much. We'll discuss in the next video.